it's in Celsius. So we are given that this piece of metal absorbs 75,000 or 75 kilojoules of heat. Now, one thing we have to be worried about is the units of energy. So because we are given, or let's just keep reading the rest. It's asking what is the final temperature of the engine part? And it gives us the specific heat of aluminum of 0.9 joules per degree Kelvin, or that could be interchanged with per degree Celsius, okay? It doesn't matter which one it is. So because we're given units of joules per gram degree Celsius, we are going to convert 75 kilojoules to 75,000 joules, all right? So this is just 75 joules. And what is that telling us? Is that not you? I guess what unit or which variable in the equation that we're going to use is that? It's not mass, right? It's not temperature. It is heat, right? So that is denoted as Q, right? So what equation are we going to want to use for this problem? Yeah, so we're going to want to use the Q equals MC delta T. MC delta T. So heat equals mass times the specific heat times the change in temperature. And the reason we're going to use this equation is because the question's asking for the final temperature, and we know that delta T is equal to T final minus T initial, right? So we can use that equation to help us get to the final temperature. So let's take a step back. If this engine part is absorbing 75,000 kilojoules worth of heat, would we say that is a positive value or a negative value for the engine? If the engine's absorbing, right? Yeah, exactly. Heat's going into the engine part. So we would write this out as, well, first let's solve for delta T. So delta T equals Q over MC. So now we can put our 75,000, and we know that's positive because it's being absorbed, right? 75,000 joules over the 295 grams, which is our mass, and then over the specific heat, which was 0.900 joules per gram times degrees Celsius. And if you put that into your calculator, what do we get for delta T?
Or
282.4 degrees Celsius, which is our change in energy, right? And we said right before this that the change in not change in energy, change in temperature. Change in temperature, which is denoted as delta T that I just highlighted, is equal to T final minus T initial. So since delta T is equal to this value, we can set that equal to T final, which is what we're looking for, minus the initial temperature in degrees Celsius, which was 13 degrees Celsius. Therefore, when you do T final, that'll give you 295.4 degrees Celsius. And you ask yourself, does this make sense? Does it make sense that the temperature rose? Right? Yeah, so it's gaining 75,000, joules worth of energy, which, is basically all being converted to heat. Therefore, it makes sense if it's gaining that energy, it's going to increase in its temperature, right? So that's how you can check to see if your answer makes sense. So T final would be 294.4 degrees Celsius. Let's do a little revamp of sig figs. How many sig figs would we have here? 3, yeah, exactly. So this would just be 295 degrees Celsius. All right. So I'll try to give y'all, I'll give you 2 minutes to work on number 48. Try your best. We'll go over it after. It's supposed to be of. It says PM, but it's supposed to be of. You were incorrect. Yep. Yeah, that's what I figured. When I did the math myself, I was like, there ain't no way. So it should be. I don't think they're gonna call themselves for it. Just trace rows or the actual. But it makes sense because this one has the least mass of KHB, meaning you should take the least volume of our solution to which means this makes sense. Especially because this one has the most at 0.42, so it's 20.9. This one's a little bit lower, almost 0.01 less. And it's 20.3. This one is almost 0.02 less. So then 19.4. So the number makes sense. Just I was and I'm never gonna try to fabricate in the team's class. All right. Keep working, guys. You're doing good. I'm gonna walk around and make one down. Flag me down if you have any questions.
I wasn't here. Because I wasn't here when you guys were going over this. I left at 3:30. I guess next time for you at 3:50.
Don't worry.
This is negative work, right? Because of the use tools.
Like just when it's negative W.
Oh, I'm saying if it releases joules to the outside of system, it's negative work, isn't it?
Yeah.
Okay.
When something releases, so work is more done by gas. When we're talking about these type of components. So because we're talking about a gas, work doesn't play too much of a role.
Okay.
Remember that's our specific. U equals MC delta T, remember? Another 30 seconds. All right, time is officially up. So guess what equation we're going to use here, guys? Should be no surprise.
U equals C times mass times the change in temperature.
Yeah, that's one way to put it. But let's just stick to what we're used to seeing, which is Q equals MCAT, just so that way we can start getting that to solidify in our minds. Q equals MC delta T. You can do your QCM delta T, it'll get you the same answer, all right? Don't even worry. So we are given a 27.7 gram sample of ethylene glycol, and it said that this substance releases 688 joules of heat. What was the initial temperature of the sample if the final temperature is 32.5 degrees Celsius? So let's start marking what we have. We have a T final this time, which equals 32.5 degrees Celsius. We have a Q of what sign would that Q be in terms of, since it's being released, is it going to be positive or negative?
It's negative.
Negative, right? We're releasing heat, therefore this ethylene glycol coolant is losing heat, right? So therefore, if it's being lost, that means it's denoted by a negative sign. So negative 688 joules. We're asked what the initial temperature is. So T initial is a question mark, and then we are given the mass of 27.7 grams. So the equations we know are Q equals MC delta T, and that our delta T equals T final minus T initial. All right. So again, similar to the last problem, using these two equations to get the answer is what we're going to do. So first, we should solve for delta T, and then solve for T initial. Or what you could do, if you like, if you prefer that, is you can substitute, since delta T is equal to this, you can substitute that into here to get Q equals MC times T final minus T initial. And then you directly solve for T initial by doing some algebra. So let's just do it this way, since we did it the other way last time. Let's do it this way, so you can pick whichever way you like going forward. So if we're solving for T initial, let's isolate for that. So, or let's isolate T initial, which is going to be Q over MC I can't do math right now. So we get Q over MC equals T final minus T initial. And then we'll end up doing T initial equals T final minus Q over MC. Right? So that's how we get to isolate the initial temperature. And then now we can just plug everything into this golden or yellow highlighted equation. So we end up with T initial equals the final temperature of 32.5 degrees Celsius minus negative 688 joules over, let's see, the mass was 27.7 grams. And then we have a specific heat of 2.42 joules per gram. And it says Kelvin, but again, this could be interchanged for Kelvin or degrees Celsius, right? So what did we get as our initial temperature? (22.24). So David says he got an initial temperature of 22.24.
Should be losing temperature, right? It's not right.
That's exactly. So I'm gonna say what you just said, David, just because that's the process that you gotta have when you're doing these problems, is asking, does this make sense? So initially David said, I got 22.24 as my answer, but that doesn't make sense, right? Because this substance is actually losing heat. So if our initial temperature was 22 and our final was 32, that would indicate that the substance actually gained energy, which doesn't make sense. So then David would but recalculate and see if you get something that makes sense. So again, this is all about making sure, does your answer make sense, not just writing the first thing that your calculator, spits out. So what is the actual final temperature each of this? Or the initial temperature? Putting that area thing into your. Anyone? What did you get, Megan? 42? Just 42? 42.2, wait. 42.7?
Yes.
Degrees Celsius. 42.7 degrees Celsius. And we ask ourselves, okay, does this make sense? What do y'all say? Someone on the left side of the room. It makes sense, right? Because our initial temperature is higher than our final temperature, indicating that we released heat, which is exactly what this problem told us happened, right? So areas that students typically end up running into some problems is when they forget to this negative sign right there that I highlighted. If you don't put that the heat is being released and denote that with a negative sign, then I think you actually get what David got, because that was your 10 degrees the other direction. So that negative has to be there. The negative has to be there in order to cancel out with the negative that's found in red, so that the math makes sense at the end of the day. All right, so are there any questions on that? Any people on Zoomy or all my Zoomies?
How many Zoomies do you have?
Yeah, 3 Zoomies today, new record. What about my roomies? We're all good. Y'all ready for the more difficult ones? Dang, already? Y'all are growing up so fast. All right,
I just got here, but sure.
that's okay. All right, guys. So I don't think y'all have done any problems like this, and believe me or not, believe it or not, I think it's very beneficial that you start doing problems like this now, because we already got 11 days till the exam. So if you start doing problems like this now, you're setting yourself up for success rather than waiting until you actually start going over these topics in class. Which will be, by then, it'll be too late, in my opinion, from what I've seen in previous semesters, because they end up going over like the final topics the day before the exam, which is not the most ideal situation. All right, so let's do one together. And then I need y'all to ask as many questions as you can, because it's all new to y'all. So maybe, try to ask as many as you can, so that way you can understand it. And then I'll have one. Question 50 is very similar to question 49. And you have a chance to see what you knew or what you learned from that first time, okay? So when 25 mils of a 0.5 molar sulfuric acid is added to 25 mils of a 1 molar potassium hydroxide in a coffee cup calorimeter at 23.5 degrees Celsius. Oh gosh, that was a run on. The temperature rises to 30.17 degrees Celsius. Calculate delta H in kilojoules per mole of water formed. And then assume that the total volume is the sum of the volumes that the density and specific heat capacity of the solution are same as water. Okay, so what is the specific heat of water that we talked about on Friday? 4.184, right? 4.184. So specific heat of water, C equals to 4.184. So we're given a lot of information here. Let's see what we can do here.
You have to find the moles of each compound.
Do we?
Never mind. Well, isn't density just mass over volume?
So density. The density only matters so much, to be honest. So, does anyone have an idea what we might do? If we're given the information of both reactants, what is something that might come to mind? Yeah, so we might have to be thinking of a limiting reactant here. So we know how to do that using volume and molarity, right? So let's go ahead and do that. So let's do that for sulfuric acid.
We first have to balance the equation.
Yeah, we can do that first. Let's balance our chemical equation. So H2SO4 plus potassium hydroxide gives us what? We have a strong acid and a strong base.
Water and a salt.
Yeah, so we get K2SO4 plus H2O. And if we balance that, we get 2 there and a 2 there. All right. So now what should we do? We already said find limiting reactants. So that's the second thing we should do. So 1 is balance that equation. 2 is find limiting reactant. Abbreviated LR, okay? So we can do that using our molarity equation, right? Volume times the molarity will give us the moles of each, right? So 0.025 liters times 0.5 molar equals 0.0125 moles of H2SO4, which is just sulfuric acid. And we know that it takes 1 mole of sulfuric acid to produce, and it can be, let's see. So the problem's asking calculate delta H in kilojoules per mole. Delta H is just the enthalpy of the reaction.
Why'd you multiply the volume by the molarity?
Volume, because remember, molarity equals moles divided by volume. So volume times molarity equals moles. So if you recall, the problem's asking for enthalpy. And it's saying calculate enthalpy, which is delta H in moles of water formed. So what we're looking for is the heat associated with this reaction for every mole of water, okay? And the way you calculate enthalpy is using the delta H is equal to the Q, the heat associated with the reaction.
You know, you're looking for enthalpy.
Because it says calculate enthalpy
Oh, okay.
per mole of H2O. All right. So this is not going to be a traditional problem that you're used to seeing, because the ones that we just gone over, we're just talking about the heat raises or the temperatures released. This is an actual reaction that we're doing in a coffee cup, and we're trying to calculate enthalpy. And what enthalpy is just the heat associated with the chemical reaction, okay? So are there any questions before we keep going? So that's why I'm converting all mine from moles of whatever to moles of water, okay? So this will give us 0.025 moles of H2O. And then we'll do 0.025 liters times 1 liter or 1 molar equals 0.025 moles of potassium hydroxide. And then it's a 2-to-1 ratio at this time. Oh yeah, you're right, I'm sorry. It's 2-to-2, thanks David. Which gives us the same exact thing, 0.025 moles of water. So what can we say in terms of limiting reactants? if they both produce the same amount of water. There's two ways you can put it. You can say that there's no limiting reactant or they're both limiting reactants. It's kind of weird how those kind of contradict each other, but that's two ways you can describe this.
What did that mean? They cancel out? Like
Yeah, exactly.
everything is used?
Yeah, so everything is used, right? So there's no limiting reactant, or therefore both are the limiting reactant. All right, so we just established that there is no limiting reactant, right? So how would we go about doing this now? Yeah. So let me shrink this down a little bit. So the way you're going to solve these problems, before we just had one single Q equals MCAT equation, right? But now, and yet this has to make sense to y'all, and if it doesn't, let me know. But the temperature of the water started at 23.5 degrees Celsius and it was raised to 30.17 degrees Celsius. So is the water going to have a positive or negative Q associated with it? If it's going from a lower to a higher temperature. Do we agree? Yeah, so it's going to have a positive Q. So the positive Q, or the heat associated with the water, is going to be equal in magnitude, but opposite in sign of the heat released by the reaction. So does this idea make sense to y'all? If the reaction is releasing X amount of heat, that means the water is gaining X amount of heat, right? Which is why it's denoted as the heat lost by the reaction is equal to the heat gained by the water. Does that make sense?
What is RXN?
Sorry, that's an abbreviation for reaction. Yeah, so the heat lost by the RXN is reaction is equal in magnitude but opposite in direction of the heat gained by the water. Does that idea make sense? Right. So now that we have that idea here, that's the same variable that we need up here. Okay. So essentially, we're going to solve for Q of reaction. Okay.
Is it equal because of the limiting reactants since they are the same?
So it doesn't equal because of that. It's this idea is just stemming from the fact that if you have a reaction that happens in water, this reaction releases some amount of heat, right? But the surrounding water is what gains the heat. So however much, if I give you 10 joules of energy, if I'm the reaction and I give you 10 joules of energy, that's negative 10 for me, but that's positive 10 for you, right? So that's why negative Q equals positive Q but they're opposite parts of the system, right? One's for the reaction, one's for the water.
Doesn't it also create potassium sulfide or sulfate? Because it creates
potassium persulfate.
Yeah, because it creates water and potassium persulfate.
You know the structure for potassium persulfate? Yeah, I don't think we'll see.
I mean, you're saying the energy produced, or the heat, sorry, produced by the reaction goes into the water, but doesn't it also go into KSO4?
No, I don't think it would, just because that's going to just remain in solution. So remember, potassium and sulfate are forming a bond. So you don't really care too much about that, okay? But if it asked about calculate delta H in kilojoules per mole of potassium sulfate, then maybe we could do that. But
I was just wondering, because it creates two solutions, and you said you only want to look for H2O.
yeah, so just asking for H2O. Yeah. So let's go ahead and get through this problem. So Q of reaction if we're solving for Q of reaction, then we want to isolate Q. We don't want to isolate, we don't want to solve for negative Q of the reaction, right? We want to solve for Q of reaction because that's what we're going to end up plugging into our formula, which is up there, right? So let's solve for that. Is equal to negative Q of the water. And we know that the Q of the heat associated with the water is equal to, so Q of H2O is equal to the mass of the water times the specific heat of the water times the change in temperature of the water, right? Okay. So therefore, we can go ahead and plug that section into our next step, right? Because the Q of reaction equals negative MC delta T. Okay. So all we need to find is the mass of the water, the specific heat of the water, and the change in temperature of the water. Agree? Yeah. Okay. So what is the mass of the water? Did they tell us?
You can use the moles times the mole mass to find.
Well, that's the moles of water formed. We're talking about the surrounding solution.
Know that.
They told us 25 mils of one solution and 25 mils of the other solution are mixed together. And that creates a 50 milliliter solution, right? And it tells us that let's assume that the density of this solution is the same as water. So how much water?
The content of water is 4.184.
So we have 50 milliliters of water. And we know that water has a density of 1 gram per milliliter. Then we have 50 grams of water. Agree or disagree? Yeah, so that's how we found the mass of water in this problem, all right? So I'm gonna try to keep everything
Only for
color
not-
coded, so that way it's easy to follow, okay?
That's only for not considering the other solution.
No, this is considering both solutions, because remember, 25 mils, 25 mils.
No, I'm talking about the product, because the product has two solutions, water and
Yeah, so we're not taking into account the water that's being formed, because that's being formed as a result of the reaction, but the heat is being released into the solution that already existed, okay? So heat of the reaction, which is Q of the reaction, equals negative the mass of the solution of water, or the mass of the water, which is 50 grams. And then the specific heat of water, which we said, which we know is 4.184, right? So 4.184 joules per gram times degrees Celsius. And then we have the change in temperature, which we haven't calculated that yet, but we were given the information, and I'm doing this in yellow over here. If you can see, maybe not yellow, student name. So delta T is equal to the final temperature minus the initial temperature. So the final temperature was 30.17.
6.67.
And the initial temperature was 23.5, which equals 6.67 degrees Celsius. So that is our delta T. So 6.67 degrees Celsius. And if you put this into a calculator, you should get that your delta, or that your heat of the reaction is equal to negative 1,395.364 joules. Right? So this is kind of just what we've been doing this whole time, using Q equals MC delta T. But we're using it in a different sense, okay?
So the reaction is losing energy while the water is gaining energy.
Yeah, and does it make sense that the Q of the reaction is a negative value when we finally solve for it? Yeah, right, because we said it's losing energy into the solution, right? So the problem, let's go back to the problems asking for calculate the enthalpy in kilojoules per mole of water formed. So kilojoules of mole per mole of water formed. Which means we need to get this into kilojoules. So there's 1,000 joules and 1 kilojoule equals negative 1.3954 kilojoules. All right, 3954 kilojoules. So that's one piece of the puzzle. We highlight it in pink. So pink is our Q of the reaction, which is what we have up here. And then our moles of product formed, since they were both the limiting reactant, they form the same amount of moles of water, right? So that's gonna go into that part there. So now we just have to plug all this information in and we'll get our enthalpy of this reaction. So negative 1.3954 kilojoules for every 0.025 moles of water formed. This gets us an enthalpy of negative 55.8 kilojoules per mole. We move that over here. Oh my God. All right. Okay, that's not. All right. So that's our final answer. And let me go through a quick recap of what we did, if y'all would like.
Sure.
Yeah. Any questions before I go through a quick recap?
You got mass again?
Mass? Yeah, so the mass of water, is that what you're talking about?
Yes.
Yeah, so the mass of water, it told us to assume that the volumes are additive, right? And that the density of the solutions are the same as water. So that gives us some hints into what to do. But the way we did that was we had a 25 milliliter solution of water, of sulfuric acid, and a 25 milliliter solution of potassium hydroxide, right? We added these two in a coffee cup calorimeter, right? So we can assume that we have 50 mils of solution now. And to get the total mass of the water in there, and we're just assuming that we're not,
Grams.
yeah,
Okay.
yeah. So,
So in question 50, the mass would be 50. Those are 20 milliliters and 30 milliliters.
20 milliliters and 30 milliliters. Oh, let's not go to question 50 yet, okay? We're still on question 49.
So the question for the envelope, for the equation for the enthalpy, so it'll always be Q reaction and then mole of whatever solution we're trying to find the enthalpy change for, or is it just for the specific?
Yeah, so it's always gonna be enthalpy equals Q of the reaction divided by moles of whatever it's asking for. So in the next problem, it'll say, calculate delta H in kilojoules per mole of silver chloride, right?
Same equation after we do the other steps.
I'm sorry, I didn't get that last
So
part.
we'll just use that same equation, just replace mole of H to a mole of silver.
Whatever, yeah, whatever it's asking for. And it'll explicitly say, unless there's only one product formed, it'll explicitly say what it wants, okay? Yeah, so what we had to bring to the table is these equations. Q equals MC delta T. We had to bring the idea that negative Q equals positive Q of something else. So sometimes the reaction is not always negative. Sometimes the reaction is actually gaining heat because it's an endothermic reaction. All right. We know, we had to know the density of water. And we had to bring delta H equals Q of reaction divided by the moles of desired thing. All right, so these are just the equations that we had to bring to the table that you might not have known about right before this problem, but now you should start committing those to memory.
VH2O.
Yeah, density of water is just 1 gram per mil. Mhm. All right, so quick recap, we first wrote our balanced chemical equation, right? And then always find your limiting reactant if you're given a problem like this. Rich can tell you all about that. So in this case, they were, you might have felt like it was a waste of time to find limiting reactants because they were both the same. However, trust me, on the test, they're not going to give you a situation that's like this. So find your limiting reactant. And then from there, establish what you need to find. So let's zoom into this equation over here. We're looking for enthalpy, delta H, and that's Q of the reaction, the heat associated with the reaction divided by the moles of whatever. In this case, they wanted moles of water formed. So the moles of water formed was found doing the limiting reactant, right? That's how many moles of water. And then next we did our Q, negative Q equals positive Q. In this case, the heat, the reaction lost energy, the water gained energy. And we solved for Q of reaction and we got that to be negative 1.3954 kilojoules per kilojoules. That's one variable that we needed to plug into that. And the other one we already solved earlier. And we just put that into the equation. Any questions before I give y'all a chance to do one more?
What do you got 9 as Q?
Sorry, what?
What do you got 9?
How did I get 9?
That's
That's
the.
Q. Oh, that's a Q thing.
Yeah, it's a Q. It's a Q.
Oh, it says it's.
So it's the heat, right?
9 over 9.
No, that's a Q, which is the heat associated with the reaction. Yeah.
The reaction is gaining temperature, so you would make the solution negative because it's losing heat.
Wait, so the reaction's gaining temperature, so that means the water would be negative, yeah, and the reaction would be positive. Yeah. So go ahead and try number 50. Be the last one. So again, these are probably the harder problems you'll have on the test, so it's good that you start practicing them now. So that way you can do well on the exam.
You know what sucks?
Nothing sucks, man.
I still write an essay for composition.
Oh, man, I haven't even taken freshman comp yet. I plan on doing that as a senior, actually.
Yeah.
Seriously? Yeah.
You're illiterate.
Yeah, okay.
And they call it freshman comp for a reason, so I guess working stereotypes.
At least you'll have an easy class for your senior.
Exactly, that's actually why I did it.
Wait, actually,
Yeah,
because I was very much taking expensive. We thought it just.
whatever your top scholar advisor says. Yeah,
No advising,
so I thought that was.
not there, other places.
I'm doing it because I wanted to get all my other art classes done earlier. And the way they have it is you do all your basics in the first year. Then you're pretty much left doing all your, like a lot of upper division classes. Like
Yeah.
maybe 3 per semester in your 4th year. Instead, I'll just be doing like 2 or 1, like final semesters.
I should shave my arts, my common arts till like the last semester.
Yeah, mix that in with all your other classes. Like, I just took a politics course over the summer because I was like, I needed to get it done, so. I'm gonna take art next semester with biochemistry too.
So smart.
All right. Sorry for distracting y'all. You wanna do this one, Rich? Let you work for the money today.
I'm tripping.
What do you think of your schedule?
Well, I was just waiting, cause like I have like. Getting what I wanna take with OCAP. Do I really wanna be writing essays with OCAP?
No.
Yeah,
That's what you did,
yeah, exactly, so I was like, oh, actually.
I have essay questions to be fair, but
Oh, yeah, if you take it with Dr. Aguilar, you're gonna be writing essay questions.
Why?
Because I have like same question in writing.
I mean, they're like short answer, but like, here's the thing, the way I wrote them, They were pretty much essays.
Just to not get the highest score for real.
Yeah, I got the highest score like 2 out of the 4 times. I wanna hear it.
If you could listen.
Yeah, we could do that. Rich could actually do that, right, Rich?
Wait, what?
You could send the PDF out to everyone.
Thought I did already.
Well, the one with all the more annotations.
Yeah, it's because it literally raised yesterday, so all of the work is like deleted.
Oh, okay, yeah. I'll send that out.
What do you get? Let me go see if that's right.
Yeah.
All right. Might want to show them the right way to do it.
All right, question number 50. When 20 milliliters of 0.2 molar silver nitrate and 30 milliliters of 0.1 molar sodium chloride, both at 24.72 degrees Celsius, are mixed in a coffee cup calorimeter, AgCl precipitates, the temperature of the mixture increases to 25.65 degrees Celsius. Calculate delta H in kilojoules per mole of AgCl produced. All right, what is step number 1?
Balance the equation.
Sure, so we're at a balanced chemical equation, so AgNO3 aqueous plus NaCl, also aqueous, gives us what? Yep, AgCl and sodium nitrate, NaNO. Aqueous here, and then it says AgCl precipitates, but we already know from our solubility rules, that's a big fat solid. All right, what is up next?
Reactant.
Yep, so step 1 was the equation. Step 2, find the limiting reactant. So we have 20 milliliters of 0.2 molar, so that's 0.02 times 0.2. So this is how many moles we'll have. If you do that, you'll get 0.004, or in other words, 4 times 10 to the power of -3 moles AgNO3. All right. So now we're concerned with what chemical? Which thing do we want to calculate the delta H of? Which thing do we want to calculate the delta H of? AgCl. So it's a 1-to-1 ratio, right? So for every 1 mole of AgNO3, there's also another mole of AgCl. It's a 1-to-1. So this is also 4 times 10 to the -3 moles AgCl. All right. So now do the same thing for our other reactant. So 0.03 times 0.1. This will give you 3 times 10 to the -3, or 0.003 if you don't like if you don't like scientific notation, AgNO3, then again 1-to-1 ratio. So for every 1 mole, oh wait, sorry, this isn't AgNO3, this is NaCl. My bad. NaCl. So for 1 mole of NaCl, another mole AgCl. We solve this out, that's 3 times 10 to the -3 moles of AgCl. So that being said,
Sodium chloride will react limiting.
yep, that is correct. So NaCl is our limiting reactant. So we'll keep that information aside for now. Now, this is what I like to call my golden principle of calorimetry. Like literally, if you know this one thing, then that makes your life a whole lot easier. Yeah, pretty much. It's like that, but for this chapter. So what's my relationship between my Q's? The Q of the water and the Q of the reaction, what's the relationship? Yeah, so Q of the water is equal to negative Q of the reaction. And since we're calculating,
There's no water.
well, in coffee cup calorimetry, there is always water.
So even if it doesn't produce water.
Yeah, because the reaction is being done in water. So like, here's like a picture of what's happening. So if I were to draw it out right here, this is like your coffee cup calorimeter. Let's just say it's like filled to here with water.
Then you add distillation.
Yeah, then you're like doing the reaction in here. So like this is your AgNO3, this is your NaCl, whatever, AgCl, yeah. Either way. So Q of the water equals negative Q of the reaction. So now here comes the time where we must solve to our heart's content. So Q of the reaction, right? Or here's how I like to do it. So negative Q of the reaction, this is going to be equal to MC delta T, right? MC delta T of water equals negative MC delta T of the reaction. So what's our mass of water in this case? 50 grams, because when we do 20 plus 30, right? That's 50, because it says assume the total volume is the sum of the volume. So 50 milliliters here. And then 1 milliliter has 1 gram, because that's the density of water. So 50 grams. So 50 grams here. What is the specific heat? Everybody knows the number, but not the units.
It's kilojoules divided by moles times K.
Close.
It's joules divided by grams times Celsius.
There we go. Joules over grams times degrees Celsius. And then for our delta T, what is our delta T? Yeah, I think that's what that's equal to. 25.65 minus 24.72.
Gives
What'd you
you 0.93.
Yeah, 0.93, that's right. 0.93 then degrees Celsius. So these cancel out, this cancels out, and we're left with joules. So, excuse me, if we were to solve this out, what we would get is,
I'm trying to find negative MCAT or positive MCAT.
we're trying to find the positive one, but here's how I like to do it. Just so y'all get multiple, like both ways. So what I get is when you solve this out, you'll get positive 194.556. But we're concerned with negative Q of reaction, right? Or wait. Yeah. Wait, let me ask you something before I. 4.184 times 0.93. Yeah, you get positive 194.556. But this is equal to negative Q of the reaction. So to get Q of the reaction, we just flip the side. So Q of the reaction equals negative 194.556 joules. So this is Q of reaction, right? We're almost there. All we need to do is say, this says what? Calculate the delta H in kilojoule per mole of AgCl. So for every 1,000 joules, there's 1 kilojoule. So if we divide it by 1,000 here, we'll get 0.194556 kilojoules. And then we'll divide this for our final delta H by the moles of AgCl produced. And which amount do we use? This one or this one?
This one.
The top or the bottom?
Yeah, bottom.
Why the bottom?
Silver chloride. Cause it's limiting.
It's limiting, so you always go with the lesser number, so, yeah, we use the bottom number, so we're gonna divide this by 3 times 10 to the -3 moles of AgCl. And if you do that, you get a final delta H here of -64.9 kilojoules per mole of AgCl. Now, let's ask ourselves, does this make sense? So the temperature went up, right? So that means my Q of reaction was negative, which we did get here as -194. And if that's negative, heat was released, and that's exactly what was reflected here.
That means actually.
Yeah, it's exothermic. Any questions about that? All right. We're gonna make like a calorimeter and y'all can exit on out of here, be exothermic.
So
Yeah.
if we were to find the Q of H2O, it would be positive 194.556.
Exactly, just flip the side.
Yeah, I got it. Does anyone plan on applying for any summer research internships?
I think it says on my schedule,
You?
but I'll see.
I think you should, yeah, you should definitely go. So the Associate Dean of the Honors College is giving a presentation on how to build resume and CVs.
Good for him.
So if you're interested in that, you should follow me to where I'm about to walk to, okay? You know.
Are you doing it today?
No,
Oh,